So, we are back with the discussion of variation principle, but before that I am very sorry I missed one small topic in before we go to variation principle. So, that topic we call it the point transformation. So, it is a very simple concept. For example, if we want to solve a dynamical problem in 2D, let us say, we can either choose x, y coordinate system in 2D plane, or what we can do is we can take r theta coordinate system, right. So, both in depending on the geometry of the problem, it might be advantageous to use one of these, but in principle we can use any of this in order to solve the problem in 2 dimension, and we can also get differential equations which will be different, of course. So, we have one set of differential equation, inside we have one set of differential equation for this. So, similarly the Lagrangian, if I write Lagrangian L x y and or rather I will just call it L, which will be a function of x y, x prime, x dot, y dot and time, and here let us call the Lagrangian L prime. So, we see that it is what we have seen, what we discuss here basically is that set of generalized coordinate, the choice of generalized coordinate is not unique. But what is important to what we notice from here, that x and y they are very strongly related to, they are related to r and theta by the set of linear transformation, that x equal to r cos theta and y equal to r sin theta, like this. So, that means although the Lagrangians are different, the equations of motion look different, but they are convertible from one into the other by using this type of relations, right. So, this is the precisely the concept of point transformation. This type of transformation of between generalized set of possible generalized coordinate is called a point transformation. So, it is basically a transformation between this set of coordinate to this set of coordinate. Now, in general, if I write this set of coordinate using q1, q2, qn, and this with s1, s2, sn, then and if there is a set of transformation equation exist which will correlate these two. So, q1 will be function of s1, s2, sn, q2 will be a function of s2, sn, similarly qn will be a function of s1, s2, sn. If such transformation equation exists between two sets of generalized coordinate, only criteria is two generalized coordinates has to be equal in number. So, if we have n number of coordinates here, it has to have exact same number of coordinates here, and they have to be related by this type of transformation equation. So, the concept of point transformation is if this type of transformation equation exists, then if L is a valid Lagrangian, L prime will also be a valid Lagrangian. Little more formally, if L gives you the equation of motion in the form d dt of del L del qk dot minus del L del qk equal to qk being the generalized force. I am just writing it in general form. If this is a valid set of equation, then this will or I should use prime here. So, if this is a valid set of equation, this will also be a valid set of equation. So, this is exactly precisely the concept of point transformation, nothing new in it. We already know that there cannot be a unique set of coordinate for a particular problem. So, there is just a formal notation, and actually it can be proved formally. We can start from this set of equation and we can show if this is a valid, if these equations exist, then also we can come to this equation. But this formal proof is more mathematical and conceptually it does not offer anything new. So, we are just keeping it. So, this is something called a point point transformation. Keep this in mind, we will solve maybe a small problem on this. Okay. So, with this we are moving totally into discussion of variation calculus, what it is, why it is useful. But before we go into all these details, I started off in the last lecture, I did some small drawing and started doing something. Let us try that. So, we define a space called the configuration space for a system, right. So, we are discussing variation principle now, point transformation is over, right. Now, configuration space is 2D space where we have time in the x axis and collection of all the coordinates qi's, okay, in the y axis. Now, this is something it might be difficult to grab as for you, this might be something very new for you. So, let us assume that I am moving this object in space or I am throwing it, it will move, right. So, it will go, it will take some trajectory, it is a parabolic trajectory, could be distorted due to air resistance, whatever it is. I need two parameters x and y, right, because it is a essentially or you can call it x and z, it is a 2D problem. Okay. Now, if I choose to draw the trajectory in real world, if I have x here, y, so we are more familiar with trajectories which look something like this, right. So, so along the trajectory the time changes, right. But if I represent it in a slightly different way, where I trace the points, trace the object whichever I throw, for example, this object as a function of time and see if its x or y coordinate is changing. If it is changing, then we move, in a certain direction, okay. And if it is not changing, we just stay at the same point. Now, this is more of a hypothetical concept, it is sometimes not very easy to visualize this, but it is more of a hypothetical concept. People use it a lot in theoretical mathematics and mechanics, and for many other even in condensed matter physics it is widely used, the configuration space. The thing is, for this type of motion there will be an equivalent trajectory which will be traced out in the configuration space, right. So, I do not know if I can draw a I can give you an 1-to-1 description of this picture and this picture, but all I can tell you, because it is very difficult to plot a variation of x and y together into one axis. But I just took a general example, it is not that it directly corresponds to this. I am saying that we are familiar with trajectories where the coordinates are changing as a function of time, but here we are and we draw both x and y coordinate, that is easy for the visualization. But we can do the same thing in principle, at least you have to agree with me that in principle what we can do is we can plot time in x axis and any variation in coordinate in the y axis, and we can represent this trajectory just like this. I really frankly speaking, I do not know how a parabola looks like in a configuration 2D configuration space, but that apart, if I do that, there will be definitely some kind of a traceable path on it. Now, let us assume that there are two endpoints. What happens is, when we throw this object, it starts at time t1, let us say, and it ends, it drops on the ground, that means or somebody catches it in the midair, that is also possible. Whatever it is, it happens at a further time t2, right. So, between t1 and t2, the entire trajectory is traced out, right. Now, we can think of a situation that due to some reason, what reason we are not going into the details right now, due to some reason the particle whichever I throw, it took not the same exact trajectory, I mean this trajectory, but it took a trajectory which is slightly different from the one. Okay. please remember, please understand that I have not changed the initial condition or anything. Okay. Or actually, frankly speaking, you can think of it this way, that I have, this for starting point and end point is the same, but maybe some initial condition, some velocity, something was different. So, that will be a trajectory which will be following this one closely, but not exactly the same, right. So, it will once again, as I said, the starting and the end point is the same, and only slightly the trajectory is different. How and why could be due to some change in initial condition, could be due to some other hypothetical reason, but let us assume that there is slight difference in trajectory. So, it will be traced like this. Now, if I zoom on this, if I zoom on this particular segment which took place over a time interval dt, okay, and try to draw it once again, what do I see? This is one segment and this is the segment in, so I will just elongate a bit, something like this, right. And so, once again we have time axis here, q axis here, right, q's. Let us assume for now that it is a one parameter system, just for simplicity. I want to demonstrate something. So, let us say there is only one parameter, it is not that system, but some other system which also shows some kind of small deviation in trajectory between two trajectories. Now, what I started in the last class, I am just drawing it again. So, I was wrong in the last class. I said that we are going only advanced, we are advancing only in time, but there is no change in q, which is wrong, because that will not give you a true trajectory. That means the object is standing in the same place for a duration of time, which is not a true trajectory, it is a static case. So, in dynamism, in dynamic case, what happens if we go from A to B, right? Let us say A has a coordinate like we did in the last class of t and q, right. If that is the case, then we have a point C, we have a point D. So, B will have a coordinate t plus, so this is dt, that is the real time displacement, and q plus dq, right. Now, if see, again it is a kind of hypothetical situation, because we cannot repeat the same time point, right. I mean, the time interval might be the same, but in principle if I throw an object and it goes to this, if an object starts from at time t1 goes to time t2, we cannot repeat it, because we cannot reverse the time, because time will always go forward, we cannot come back to point time t1 once again. So, it is kind of an hypothetical situation. So, if let us say hypothetically speaking, the object could have taken one of these two trajectories, right. So, this is a more correct statement, the object could have taken one of these two trajectories. Now, if that is the case, then the displacement from A to C is actually a virtual displacement, right, because it is taking no time. It's either could have been this or could have been that, whatever it is, between these 2 points there is a virtual shift. But virtual shift means C will have a coordinate t and q plus delta q being the virtual displacement, right. So, we have coordinate for A, B, C. Now, what will be the coordinate of D? I can go from A to D either like this or like this. So, we can take A, B, D, or we can go A, C, D. If we go A, B, D, the coordinate of D will be, if I take A, B, D, coordinate of D will be, again B to D is another virtual displacement. So, same time, okay, so forget about the time part, time will be the same. Whether I go from this way or that way, time will be t plus dt. There is no doubt about it, only the spatial part I am interested in. ABD, the q coordinate will be, so like this will be a virtual displacement of q plus delta q, q plus dq. So, it will be q plus dq plus delta of q plus dq. Similarly, if I take A C D, see C to D is a real displacement in time, right. So, it will be q plus delta q plus d of q plus delta q, right. So, once we compared this, and but d will have an unique coordinate, right. I mean the coordinate of d, whichever path we take, it should not alter the coordinate of d. So, comparing this to this will be equal. Okay. We will see that all the terms will cancel out. If I open this bracket and perform, there will be a dq here, right. So, if I open it, it will be a delta q here plus delta of dq, and there will be a dq here plus d of delta q, right. So, if I take, I mean if we equate this to this and this will cancel, remaining will be delta dq plus, which will be equal to d delta q. So, what we have established here is by taking two hypothetical trajectory of a system between two fixed points T1 and T2, that the operations d and delta which can be exchanged freely. So, they are commutative basically. So, d of delta q is equal to delta of dq. This is a reason, this is a result we have already used it. We have, if you recall, if you go back to the derivation of the Lagrange's equation, we have already used it. But now I thought I will give you a proper, what do you call, elaborate, I will elaborate on this point and give you a proof of that. Now, but this is something that has come out as I would say as a side talk, I would rather say. What I want to discuss actually, so I demonstrate this for a single parameter system. It might as well be extended for a multi-parameter system. That is not the problem. Now, what I am trying to demonstrate here is possibility of having various paths between two fixed point T1 and T2 of a particular system. So, let us have a situation. We have a system at time T1 which has a particular orientation or particular set of coordinate which corresponds to a point, fixed point. So, this is my point 1 in the configuration space, and I know after certain time gap, it will at a time T2, it will reach a point, fixed point 2, between which has a time T2 and a coordinate Q2, which is a point 2. Now, in between these 2 points, which path the system takes? That is a question I am asking here. Okay. That is a question I am asking, and not only me ask, I mean it is not that I am asking it, physicists has been asking this question for centuries. So, the first, okay, so the problem in a more physical manner, the problem is following. I have a object in my hand, I drop it and I catch it here. What makes it travel in a straight line? You might say the gravitational pull, but that is not precisely the answer, because whatever path it takes while coming from here to here, if it comes like this, if it comes like that, take any other path, the initial and the final energy states are the same. Similarly, if I am hanging a chain, you must have seen that this electric lines, high tension lines between two poles, they are not straight. There is a, it due to gravity, they have a particular curvature, I mean particular shape, and that shape is very well defined. You hang a thread, you hang a solid chain, you hang a plastic pipe, it should take the same shape. I mean, it should follow the same family of curve. I mean, you have similar types of equations. What makes it take that shape? It could have taken any other shape. So, there must be some parameter which is being optimized. That was the question physicists were asking for centuries. It started with Fermat. We all know that Fermat principle, right? What was the Fermat principle of least time, that he was the first one to give some kind of an optimization principle. He said light will travel between 2 points along a path which will take shortest time. He never used the word straight line. It happened to be that path is a straight line, because shortest distance between 2 points in space is a straight line. By the way, have you ever seen, we all know that, right? The shortest distance between 2 paths is a straight line, the 2 point in space is straight line. Have you ever seen any formal proof of that? No, right? We will prove it. There are ways of proving it using this variation principle, right? So, then when it comes to, Fermat came up with this principle of least time back in 1600, year 1600. That time the classical mechanics was in its early age, before Newton. So, we did not have much idea of modern mechanics, modern equations, but when that came into picture, then people started asking why a mechanical system takes a certain path. For example, when I throw this chalk, it will take a parabolic arch. Why a parabola? Why not anything else? What makes it take the shortest? What makes it take that particular path? So, something must be, it's not a straight, it's not the shortest time path, because shortest time path between any 2 points will be a straight line. That is very intuitive. Of course, it might not be true all the time. Okay. So, why a parabola? Why not any other curve? So, then in 1744, almost at the same time, Euler, the great Leonard Euler, and another French scientist, Morpetius, they came up with a principle which is called the ancestor of the so called principle of least action. What they said was, actually Euler said the mechanical system will follow a path along which the quantity integration m v ds, s being the length along the curve, arc length, v is the mass, m is the mass, v is the velocity, where along. So, according to Euler, that was in 1744, two independent minds, one sitting in Germany, one sitting in France. Just a minute. So, So, the pronunciation in my opinion will be Mauperti. It is a French name, Mauperti, but do not count me on this, because do not quote me on this, because I am not an expert in French. Anyway, so and he said, oh, no, the path which will be taken is along which the integral, the path integral. So, this is the path integral, okay, along which the path integral c 2 times t dt will be optimized. So, they came up with these two suggestions, but then if I slightly manipulate it, if I put dt, this is nothing but v, okay. So, this will be v square and mv square is nothing but 2t, right. So, from here, so these are actually equivalent. So, this is nothing but mv square dt, which is 2 times t, the t being the kinetic energy. So, they came up at the same time with the same principle. But even at that time in 1744, the formal approach of Lagrangian calculus was not formed. Later on, Euler had a great role to play in the derivation of Lagrangian dynamics, but he somehow could not make a progress from here. What he derived was very true, okay, not very true, but at least for certain system it is right. But then we have to wait for another 100 years. Then the Lagrangian dynamics was was formulated, and then people started working on that more and more, and then came this very famous very famous Irish scientist whose name is Sir William Rowan Hamilton. That was, he lived between 1805 and 1865, and he actually kept on building on the Lagrangian dynamics and developed something called the Hamiltonian mechanics, which unfortunately we cannot discuss during this course, which our course duration will not allow us a discussion of Hamiltonian dynamics, but whoever taking an advanced classical mechanics course will start with Hamilton's principle. Now, he came up with a principle of stationary action, or sometimes called the least action. What he did, he replaced this kinetic energy term, okay, with the Lagrangian of the system, and between two time points t1 and t2, the system will take that path along which this particular integral L dt is stationary. What is the meaning of stationary? Stationary means the variation of that integral along a particular, if a variation of that integral along a particular path is 0, the system will follow that particular path. Okay. So, what it did essentially was replace this t with t minus v, that is Lagrangian, right. So, the principle of least action or principle of stationary action says action, okay. So, this is a quantity. Action is this particular integral t1 to t2 L dt. A system will take a path along which variation of this action is equal to 0, and we see that this delta operation, the variation operation, is interchangeable with derivative. It is very much like a derivative action. So, that means the system finds a path along which action is minimized. Okay. So, action is also a function. After this integration also it remains a function of certain parameter, right. We will see that how to work with on that. So, what we need to, so what in the framework of variation calculus, what we deal with is we try to determine the variation of such integration. And so, first what we will do is we will take any function which might be a Lagrangian, might be something else. Then we will see that in special case of Lagrangian, this equation, when we set this equal to 0, is actually give us back the set of Lagrange's equation of motion. Okay. So, let us try that. Keep this in mind. I am going to remove it now, but I hope you already have your notes. So, we will start it little more formally. Now, in order to understand the variation in a more fundamental way, what we are going to do is we will say that there are many possible paths which are infinitesimally close from one another. Now, out of that path system will choose one, but right now let us not go into which path the system will choose. That is more I mean, let us concentrate on how to formalize this little bit. So, let us assume what happens is each of this path which are slightly different from each other, where the coordinates will also be slightly different, right. So, what we can do is we can write any coordinate q I as, or q I, which is a function of t, and we introduce a new parameter alpha, which is also an infinitesimally small parameter, and we can write the coordinate as 0 plus alpha eta t. Okay. So, what we are doing is we are decoupling the time variation of a particular coordinate. What is changing between two paths? So, please understand that as we move from one path to the other along this line, along the t, I mean along a path where t is fixed, these are all virtual displacements. So, we have to somehow formalize the virtual displacement of delta q. How can we do that? Please remember, in delta q there is no t evaluation. So, we have to decouple the time variation and spatial variation of each and every coordinate. In order to do that, what we do is we actually introduce a new parameter, infinitesimally small parameter alpha, and take a Taylor series expansion of q around alpha. So, q of t alpha, if I take a Taylor series expansion at around alpha equal to 0, this will be q of t alpha equal to 0 plus del q del alpha at alpha equal to 0 d it will be alpha plus 1 by 2 factorial del 2 q del alpha square at alpha equal to 0 alpha square and terms like that, right. So, this is a standard Taylor series expansion. Because alpha is infinitesimally small parameter, what we did, we essentially truncated this here and we ignored any parameter, which has order alpha square. Okay. So, comparing these two equation, we see that eta I t is nothing but del q del alpha at alpha equal to 0, and what we can see is delta of q y will be nothing but delta of q y t 0 plus or delta of the or virtual displacement of q y will be nothing but alpha n I t. So, this is an infinitesimally small variation of the function of a function which depends explicitly on time, right. So, we can write it in this particular form. If this is the case, then the time for generalized velocities we can do the similar construction, like if I take a derivative of this, time derivative of this, we can write q y dot t alpha is equal to q y dot t 0 plus alpha eta I dot t. We can do that. And once again for generalized velocity also delta q I dot is equal to alpha n I dot t. So, once again what we did is we have decomposed t into a q into a time dependent part and another part which does not depend on which and another part which is a function of a quantity which does not depend on time, but defines a spatial variation, right. And so, that is why the virtual displacements can be written in this particular form. Now, we take any function f which is a function of q's, qy's, qy dots and time. It could be a Lagrangian, it could be any other function. So, let us take a general form and we have to define and we have to let us say this this integration exists which is between t1 and t2 dt, right. Now, what we have to do is we have to take a variation of this integral. Now, what happens is this integral, if you see q's are function of t and alpha, qy dots are also function of t and alpha. So, if I integrate the time part, what remains is this integration is actually a function, the final after this integration what remains are the alphas, because alphas are not integrable, alphas does not depend on t. So, we have I of alpha. So, what we can do, just like we did in the case of coordinates and velocities, we can also expand this integral in a Taylor series around alpha equal to 0 and we have del I del alpha equal to 0 alpha and we can neglect the higher terms. So, the variation of this integral d of I alpha will be nothing but alpha times del I del alpha equal to 0, right. Just like we have variations in coordinates and velocities, we have a variation in this integral and this is precisely what we are looking for, right. Okay. So, del I del alpha we have to evaluate, in order to evaluate the variation in the integral we have to evaluate this term del I del alpha. So, del I del alpha going by this is nothing but t1 to t2 f of So, it will be del f del qy del alpha plus del f del qy dot del qy dot del alpha plus del f del t del alpha, right, integration dt. Now, the last term of this differential vanish, because alpha and t, the alpha is not a function of time. So, del t del alpha or del alpha del t is equal to 0, right. So, the last term is actually a 0. Two terms remains, and in these two terms what we can do is we can this will be evaluated at alpha equal to 0. So, all these derivatives at alpha equal to 0, right. Now, if you recall, dqy d alpha equal to 0 is nothing but your eta I, right. So, that is what we did just now. This quantity is your eta I, and if I multiply this with alpha, so we have a multiplication of alpha here, we have a multiplication of alpha here, sorry, we have not enough space, but you understand, right. So, we have to multiply this whole thing with an alpha, this is anyway 0. So, alpha of this will be alpha of del qy, alpha multiplied by del qy del alpha is equal to alpha times eta I, which is equal to delta qy, right. So, this integration takes the form integration T1 to T2 del f del qy. Oh, by the way, there is a summation over qy I parameter, I mean this index, because it is a repeated sum which is implicit in this delta qy, and similarly we can do the same thing for the generalized velocity component, and this will come out to be del f I del q dot delta qi dot, right. And this in short can be simply written as T1 to T2 delta f dt, right. And this is nothing but variation of I. So, this is equal to this. So, what we have seen is if I is this integral, then variation of I is the variation of this parameter, and this is kind of intuitive because integrand is what defines a derivative, integrand is the main part of the integration. So, this is fine, but then we can take it 2 steps ahead from here. What we can do is we can continue here from this particular form, that delta I is equal to integration T1 to T2 del f del qy delta qy plus del f del qy dot delta qy dot times dt. Okay. So, this and there is a summation over qy, and from here we can, okay. So, there are two or three more steps which I will continue in the next lecture.